Welcome to this lecture on applied statistics. We will cover linear regression, multiple linear regression with many covariates. And this is a very important topic in statistics. It's the foundation for many recent machine learning methods, and it's often doing an extremely good job in applications. The focus is on chapter 11 and 12 in this book that we're using in the class. To motivate the situation, consider the following dataset of many different countries, and the two data are cigarette consumption and CHD mortality in the different countries. And we see at this time, back in the 60s, the United States smoked a lot of cigarettes, 3,900 per adult per year. That's quite a lot. And what we're interested in is then the CHD mortality per 100,000 inhabitants. And in particular, we would like to see if there's a connection here between the cigarette consumption and the mortality rates. And this is a typical example of regression analysis. We have some inputs called covariates. Here there's only one. We could imagine that there were others as well, some economic indicators, eating habits, alcohol consumption, etc., training, lots of covariates we could imagine that also have an effect on this response, which is CHD mortality in this case. Okay, the first task in any kind of regression analysis is to cross-plot the data. And here we have cigarette consumption on the first axis and CHD mortality on the second axis. And it seems to be a relation here. So if we put a line through the data, this line would have a positive slope. And this means that if you smoke more cigarettes in a country, that country has a higher number of mortalities caused by CHD. So what we're then doing in linear regression analysis is basically to try to fit a line here. One way or another, we try to fit a line going through the data. And there are many ways of doing this. We will focus on one method in particular called the method of least squares. And this is minimizing the vertical difference between the data points and the line, the predicted line. And as I said, this is only a cross plot that's easy to make with two variables when you have one covariate, cigarettes here, and one response, CHD. But you could have many other covariates as well. And then it's common practice to cross plot these to get some idea of what this might look like. And quite often you then discover that you have to transform variables one way or another, take logarithms, truncate one input, combine one input with another. And this is then still considered linear regression. It's just that you have other response or factor variables that you have engineered, or you've created what's called sometimes features. Okay, so what is this thing assuming? We're assuming that we have some response. So this is again the response variable. And in the model, we say that this response is regressed on some covariates. And to indicate the weight on the covariate, we have these regression parameters. And that's what we will estimate. This is the slope of certain inputs. If we smoke one more cigarette per day, how much does that influence the CHD mortality? That's the beta slope. Epsilon is a noise term, and we will later assume that this one is Gaussian distributed, independent, with a constant variance. And those assumptions have to be checked again with cross-plot like methods. Quite often you'll see that this is written in simpler forms, and then we write yi equal to beta 0. This is then the intercept, which does not have anything to do with covariates. And then you regress this beta 1 x I1 plus and so on up to beta k I xik plus epsilon I. So this is now the regression on covariates. So these are the slopes with the different x covariates. And what we have then is typically a data set of y, x1, x2, x3, up to xk. And we have this for many I, from I1 to n. So then we can collect this in matrix vector form, and that's what's done here. Here we have y1, yn, and we model this through some matrix x11 up to x1k, all the way down to 1x n1 x n k, and we put up these regression parameters like this, and then we have the noise term. So this is our X matrix of regression inputs. So that's how we model this. This is our assumption going in here. We assume the data can be regressed linearly on some covariates X with noise. The next question is then, okay, how can we fit a line? So for me, if you have just one covariate, you can easily sketch a line, and that's what I did here. This looks good, but why is that good? I could also sketch this line. Why is that bad? Or this line. So the solid line in this diagram is going through the data points. So it's not going through every point exactly, but it's capturing the main trends in the data. These other two are pretty far off, I would say. And in a sense, we're here minimizing what's called the square errors of the line. So this is now a data point. This is xi. So this is xi, and this is yi. Whereas this point, what's that? This is for the same x. But here we have a prediction that we will call y hat I. And this distance is then sometimes referred to as EI, as a empirical residual in the model. We take the data and we look at its distance from the line. We have the same here. This is another pair. This is another EJ, if you like, another empirical residual. So to get the best line, we then minimize the sum of square residuals in this way. And that's what's done over here. And for this particular regression model with just one covariate and an intercept, this would be equal to the sum over all data pairs, yi minus b0, so that's the intercept over here, minus b1 xi. And b1 is then the slope. When we smoke one more cigarette, how much does that influence the CHD mortality? And here I'm using B instead of beta. So beta is something theoretical in our model, a statistical construction. This B is sometimes we can compute from the data, and it's our estimate of the line. So by minimizing this with respect to B0 and B1, I find the best line, and I would pretty soon sort of reject these. They have large errors, so they are poor fit, whereas this line is a good fit. This can also be done on matrix vector form. So instead of writing this sum over I from 1 to n, we could write it as we've done here. So then we say that, okay, here's our vector of response variable. This is our matrix of covariates, and this is B that we want to estimate. And when we estimate something, we then say, okay, we want the best line. So that means we minimize this sum of squared errors. And how do we minimize? Well, one common way, and that's what's done in mathematics, is to take the derivative and set it equal to 0. And that's what's done here. We take the derivative of this quadratic form with respect to b. And so the quadratic terms become linear. And then we also get one term without b here because that just canceled. And when we set this equal to 0, we get this solution. This is the least squares estimator. And here I'm writing small y, but so this would be an estimate. If I plug in my model here and consider the y to be a random variable, like a capital Y, then it would be an estimator, something that we can also study the statistical properties of. So this is parameter estimation, and what we get out is then this fitted line. And the properties, as I said, can be extracted from the modeling assumptions. And what did we assume in our model? We had this error term, and the error term was supposed to be Gaussian distributed. So this is what we're using when we say modeling assumptions, what's going in here. So first of all, we assume that this error term is zero mean, and we say it's independent and that they all have the same variance. And this is something we can then go and check in practice. And how do we do this? Well, now in our estimation procedure, we don't have this one. We only have an estimate of this. So we estimate beta by B. And then we get y hat I, which was xib. And hopefully then if we start to look at differences here, these residuals, which are not theoretical residuals like these epsilon, but these are data residuals. We hope that this difference also has similar properties as the epsilon. So we hope that these are also more or less independent, more or less have the same variance, and so on. And this can then be checked. So we can check these assumptions. And what's commonly done is to use a residual plot. And then you make histograms of the residuals, and you plot them according to the normal distribution, what you would expect there. You plot them with the response, or you plot them with the observation order, or other things, or with covariates, for instance. And in this case, I think it looks pretty good. What is not looking good is if you have a tendency of having something like this, maybe that might indicate that there's more variability in this part than in the other parts. So this is sigma square is maybe not constant. And if this is not constant, perhaps we should account for this in our way of constructing an estimator B, because we say that all these y minus y hat should be weighted equally. But maybe that should not be the case if the noise is not the same. We could also have plots that indicate correlation, say if there's something with a measurement order being done at day and night and so on. So this might be something like this. So this is not independent. This is correlation. So correlated epsilon. So this indicates correlated epsilon. And again, maybe this should be accounted for in the sum of squared errors that is used for least squares estimation. Again, this does not mean that we will weight every sum equally. Instead, we will have things that are very correlated, a bit downweighted, so that they don't count twice or 3 times. Okay, so if these assumptions hold, then it's easy to compute the properties of the estimator. So this is the estimate when I plug in y, but I can also say that an estimator is b equal to x transpose x inverse x transpose y, where this y is now considered a random variable. So it has an expectation, it has a variance, and it's Gaussian distributed because these epsilon are Gaussian distributed. And then we can compute the expected value of b, which is this thing in front here, and then times the expected value of y. And the expected value of y is just x times beta. And now you see that x transpose x cancels. So this is just equals beta. And in a sense, this shows that the estimator b that we get from least squares by differentiating these sum of squares is unbiased. On average, we hit the right target. The variance of b is slightly more complicated, especially when we write it in this vector matrix form. So usually when you take variances, you take a constant outside and you square it. But when you have vectors and matrices, you take the matrix outside, but then you also transpose it and put it on the other side. So if we do that here, we get x transpose x inverse x transpose, and then the variance of y. And then here we get x transpose x inverse, where I have transposed the first part. And what was the variance of y? Well, that's sigma squared, the variance of epsilon, and they are all independent. So this is the identity matrix, no correlations. And when we plug in this, sigma comes outside. We see that 1x transpose x cancels with this inverse. And then we have, in the end, x transpose x inverse. And in this case, with 2 covariates, we have then a 3x3 matrix indicating this variance and covariance entries of the parameters. So this would be for the intercept, and this would be for slope 1, and this would be for slope 2, and the same in the rows. So this is the variance, or not the variance, but up to a proportionality constant sigma, and then slope 1, slope 2. So the variance of slope 2 is here, up to a normalizing constant sigma again, and this is the covariance between the 2 slopes. And these covariances are quite important because sometimes we have covariates that are almost identical, and then it turns out that the rows in this matrix are sort of almost the same. They're linearly dependent. And perhaps then it's not worthwhile to have all the covariates in the model. Actually, you might be just as well off without one of them. This is called collinearity. And we will get back to this in a few minutes. Okay, so this is good. What do we usually do in statistics when we know these properties? We go on to do hypothesis tests or construct confidence intervals. It's one more thing that's required, and that's to estimate sigma squared. It's usually not available here, so we have to estimate it, and we use the usual s squared, but slightly shifted because now we construct it from the residuals. So s squared is then the errors away from the line. So we have these plots, and to compute s squares, we look at these distances, ei, ej. How big are they? And that shows the variability around the line. And then we normalize not with n or with n minus 1, but actually with n minus k minus 1. The reason for this is that we've already used k plus 1 dimensions of the data to estimate k slopes and 1 intercept. So there's only redundancy of n minus k minus 1 degrees of freedom left. The t-distribution is then used to construct hypothesis tests or confidence intervals. And here's an example. Let's assume we want to test if the slope of a certain covariate j is equal to some fixed number that we know, beta j0. Well, then we can construct a test statistic, and this test statistic is then under h0 because you see we plug in this hypothesized value under h0. And then we normalize just like we do with the t-distribution and the normal distribution with the standard deviation, which is S that we have computed, and then the diagonal of this X transpose X inverse matrix with a square root. Because it's not variance, it's standard deviation going under there. Okay, we don't often compute this ourselves. We use some software. And here's a printout from Minitab where we have done this hypothesis test. And our beta J0 in this particular example is 0. So we test this one equal to 0. So this means T is B CJJ. And here we test for the one slope that we have. So here it's B1 S C11. And we saw that this one is B1. And this number that we have down here, so this is again B1, the estimated slope with respect to cigarette consumption. SC coef is then S square root C11. And the T value in this case is quite large. And since it's so large, it's far out in the tail of the T distribution, and that gives us a very small P value. So again, recall the T distribution. 0 is here, and then we observe something way out here in the tail. This is our T value, 4.65, and there's a very slight chance of being out here. And we have the same at the other end, minus 4.65. And in the end, the P value is then this area on both sides, which is very small. So what happens here? Well, we would reject H0. The p-value is small, reject H0, and we say that, okay, smoking a lot of cigarettes is not good for your health. At least when it comes to coronary heart disease. That's what we're looking at here. We could also do this with other covariates. So here is a local example from Trondheim where someone has been running with an autonomous underwater vehicle like this to collect salinity measurements near the river. And then it was going somewhere along here, I think, starting here and then going in the east direction, a bit north, but not so much. You can cross-plot salinity with north and see if there's a connection. Not that many measurements here. I think it's how many? 1, 2, 3, 4, 5, 10 measurements. But it doesn't seem to be much of a connection between north and salinity. Between east and salinity, there clearly appears to be a connection. And the reason, sort of the biological or the phenomena here, is that the river comes out here. So the river is, of course, fresh water, and then it starts to mix with the fjord waters. So you would expect the salinity in this part to be smaller than over here, and that's what we're seeing. But maybe the north coordinate is not so important in this analysis. That's what we can study by fitting a regression model. Then we test for both covariates, both slopes, and maybe also for the intercept. Is this significant? And again, let's use Minitab. Minitab first fits the line. This is B0, B1, B2, the slopes with the different inputs. And then we see the t values and we see the p values. And the p-value for east is very small, so we want this in our model. There's clearly an intercept that we benefit from. This fits the data quite well. But the north coordinate is having a large p-value. And then the natural question is to ask if north could just be ignored. Is it relevant? Perhaps it doesn't increase our predictive abilities when we use this model. Okay, what is plotted here is, or what is written out is the fitted line. So let's go on to estimating the line. So this line can be interpolated between data, and it can also be extrapolated to some extent away from the data. And typically one is interested in predicting at some new covariate. So here x0 is a new input or new covariate. And we want to predict this. So y hat 0 is new prediction. And in doing this prediction, we then use our model. So we plug in for B. We know that B is unbiased. So if the linear regression holds, this is also unbiased for the line. We can compute the variance because we know the variance for B. And this is what we get then. This is often used to create a confidence interval for the line. So that means we can draw a line and then have some confidence bounds around the line. What is equally common to do is to predict a new observation. So then we look at this difference, again, a residual, but here we don't have a real residual because we don't have y0, but we want to have a prediction interval for y0, and then we can sometimes say, oh, wow, this was far out in the tail, or, okay, good, this was within the reasonable variation that we expected. So this expression can also be used to come up with what's called a prediction interval, which is slightly wider than the confidence interval. Sometimes it's actually significantly wider, and that depends on the difference between sigma compared with the x transpose x matrix. Because what's added here, going from the red prediction interval to the red prediction interval from the cyan confidence interval is a sigma term. We also see the data representation in this plot. So we see that here the confidence interval is much narrower than out here. And that's because most of our data is around the center. There's some data out here, but it doesn't help us so much to know the slope here. So given our uncertainty in B0 and B1, there's quite some variability here. So this line would also be good, and this line would be good. So when we draw different lines through the data, that could also explain, well, we see that there's smaller variability here than up here, and same here. Since sigma is relatively large to X transpose X, we don't see the same difference in the red one, but it's there to a smaller extent. This thing about line prediction can go a bit further. And I said we could use this to come up with surprises. So now we have a prediction interval and we get a new measurement. Sometimes it's far outside what we expect. Then we can also do this for the data that we have. We have a prediction there. We saw this before. I was drawing a line going through the data. So for this X, I now have this one, which is Y hat, and I have this one, which is Y. Let's call them yi and xi. So by just plugging in for the regression parameter b, here we have this b, and then we can collect all the x into the matrix H, sometimes called the hat matrix. This hat matrix has certain properties that are appreciated much in mathematical statistics, and we won't go into the details of this, but it's important for us to look at the difference between this age matrix that's using the covariates and the model that would just take the mean. Because that's the alternative here. This is doing the same thing. So remember that we had here x transpose x, and then inverse x transpose y. Here we get a similar thing, but we're just taking the mean. So we're taking the mean, but we can write it in terms of one vectors like this. So here this one, what is that? Well, one is a vector of one entries. Just the intercept, if you like. No effect of the regression model, no effect of the covariates. So we have two ways of predicting here. X, Y, we have lots of data. A regression analysis would then fit a line like this. It's not a very straight line, but it's supposed to be a straight line. This is Y hat, which is then this matrix age times Y, projecting the Y into the line. The alternative, as I tried to say, is to take the mean value. Then we just look at the data mean. Perhaps it's here somewhere. This is Y bar. This is our prediction. So we can call this Y bar GY. And that's what I'm trying to indicate here. For my drawing, it would be really silly to use the mean as a prediction instead of using the Y hat, which is based on the regression parameters. But this is not always the case, especially like we saw in the salinity example, you had many X and maybe only some of them were relevant. So then you can imagine doing this sequentially in some way to try to extract the important variables. But first of all, you should see that your regression model is doing a better job than just using the mean, which is extremely simple and would mean that you don't have to care so much about these covariates. So this is sometimes done in hypothesis testing as well, where we check age 0 the hypothesis saying that all slopes are zero. There's no effect of the covariates. To test this, we can break down the data variability in different parts. So here is the sum of squared total errors, where we take the distance from the data to this. So here's our data. Here's y bar, here's y hat, this is y. So to look at the distance from y to y bar, we just take this sum. This is the total sum of squares. When we fit the best regression model, we computed the sum of squared errors, which is the distance from the data points to the predictions. And for most data like this one is then EI, whereas this one is the distance down to the regression line. For this one, it might be better off if you just use this one, but of course you never know. On average, it's always better actually to use the regression model with covariates. But is it significantly better, or is it just luck? That's what we can try to break down a bit. If you want to look at this in terms of matrices and vectors, you can write the sum of squared errors on matrix vector form. You can write the sum of squared errors on matrix vector form. And they have some nice mathematical properties, as I said. These sum of square errors can then be split in different parts, where we first look at the regression sum of squares, and that's the difference from the prediction to the mean. And then we have the error sum of squares that we use to fit our regression model. This is the distance from the data to the predicted regression model. And then we have the total. And these can be written or projected in these matrix models. These sum of squares are very important not only for regression analysis, but also for other branches of statistics. It's a way of splitting variability in different components. So it's very, very useful. For our case, it's important to notice that the sum of square total errors can be split in two components, and that's the SSR and the SSE. So SSR, as I said, is the distance from the regression model to the mean. And you can imagine if the regression model is doing a really good job, so y hat is close to y, then SSR must be close to SST. Because what was SST again? SST was the distance from yi to the mean. And in SSR, we look at the distance from y hat to the mean. So if the regression is doing really well, y hat is next to y, then this would be capturing most of the variability. This would be close to SST, whereas SSE is much smaller. So SSE, what is that? That's the distance that we had in the residuals. Okay, many SSE, SSR, SST. Okay, splitting variance. And this R squared that we have here is always between 0 and 1. It can never be larger than 1 because SST is SSR plus SSE. But we want to have a large R squared. That means our regression model explains a lot of the data variability. If the regression model doesn't explain much at all, it just slightly explains more than just taking the mean, then SSR is close to 0. These two are almost the same. So that means R squared is close to 0. There's no kind of predictive element in the covariates. To formalize this, we can again do hypothesis tests, not on R square, but a related quantity. And that's what's done in to test these hypotheses. You take the sum of regression sum of squares and divide it on k, so that's the number of covariates. You take the residual sum of this error sum of squares and divide it on the remaining degrees of freedom, and this is basically S squared. This is now Fisher distributed with certain number of degrees of freedom. And the Fisher distribution can be calculated, and then we can check, okay, this is our percentile alpha in the Fisher distribution with k, so that was the number of covariates, and n minus k minus 1, that's the degrees of freedom left to estimate the variance. This region has alpha probability, and this is our rejection region. What does it mean here to go reject when f is large? When f is large, SSR is large, that means the regression explains a lot of the variability. To make f really large, you can also make S squared small. That means the y hat is close to y. So clearly then the regression has an effect. This H0 is not true, so we reject this. Should we do this for the salinity example? So first then we test, okay, what is R squared? This is R squared is really large, 90% or 0.92. This is S, so that's the square root of S square, which is equal to the square root of SSE, and then N minus K was 2 plus 1, so 3. To test the hypothesis, we use this Fisher value, which has then 2 degrees of freedom and N minus 3. So that would be 2 and 7, since N was T. And we observe this Fisher value, which has a really small p-value. And this tells us that the regression model has an effect. It's still not clear if this north coordinate has an effect. Then we need some more knowledge about these things. But it turns out that north here is not relevant. It's only east that helps the explanation. North that does not significantly explain more. Right, let's go on to say something about regression parameters, because now we talked about these slopes. Are they significant? Are they not? Should we maybe transform some of these covariates, because we see from residual plots that they might be better off if we change them. So to do this kind of model fitting, we always want to strike a balance. We want a simple model with few covariates. The simplest is the mean, but maybe we can go a bit further than this. But we don't want too complex a model either, because if we have too much complexity, we might start to overfit to the data, and we do a sort of go through the data points. That's not so good either. So a typical example of overfitting is that in this case, what can we do here? Well, I can write a model that's y beta 0 plus beta 1 x. But why only use x? I can use x squared. I can continue. I can use up to kxk. So this is a polynomial. And if you start using polynomials, you can fit a lot here. So instead of fitting a simple line here, you can start going through the data like this. But it likely leads to overfitting. You've done this exercise. Perfect fit. There's hardly any error here. But then as a consultant, your partner tells you, oh, there was this one data point I forgot to tell you about. Oh, well, I'm sure it would fit on my line, but then he says it's here, and you miss quite dramatically. So this is overfitting. So you want a simple model, but not too simple. You want to capture the things that are relevant. In particular, like I said here, you want to do well on unseen data or a holdout set of data. And what we typically do here is to play with covariates, bring them in, out of the model to see what gives us a better fit. And I thought I would demonstrate this on this example that indicates infant lengths and is regressed on some covariates. And I can show you this in Minitab. So here is our data, and then we can do statistics, regression analysis, fit regression model. And my response is the infant length, and I regress these on some of these covariates that we have. And here you see that there's also an option of stepwise regression, but I use none here to begin with. So I can compute this, and Minitab tells me, okay, for this example, with my 4 covariates, it turns out that the p-values, if you look at this, is the best for weight, but none of the p-values are standing out here. So not a whole lot of predictive power maybe, even though R square is very large. So it's not, everything is not there. It's not obvious to interpret these things. You have to look at a combination of things. Analysis of variance, this F value is huge, so clearly combined these regression inputs, the covariates explain a lot, and we won't use only the mean. And that's also what the R square says. We can do much better than the mean. So in analyzing this, we can then do what's called stepwise selection. And if we only look at one covariate here and try to regress one on one, not 4 like I did, but do only one at a time, then we can check which one is the most important. And here it turns out that the largest SSR, so what was that? SSR. So SSR is then the sum of yi minus y hat I y bar. Which one gives me the largest SSR here? That's covariate 1. And what's then my model? My model is y hat I fit B0 and then B1 x1. I don't have any more. This is all I got. And then I get the highest R or SSR. I also do the same for only 2, 3, and 4, but then I get smaller numbers. So this stepwise selection method is then going forward, and here it says that, okay, this covariate was significant. We get a good F value. It gives a small p values. So we bring this into our model. And then we can continue like this. Now we took the single best covariate. We can then try to add one more together with this first one we selected. Is this also significant? Then we go on. And then we try the third one. Does this add something when it's combined with the first 2? Then we add it, otherwise we stop, and we go on like this. So this is called stepwise forward selection. And here in Minitab, we see that the first one is significant. And then also the third one turns out to be the best one combined with 1. So we have 1 and 3. But then we see that, okay, when we now try to add 2, it's not giving a very big value. And when we try to add 4 with 1 and 3, it's not giving a big value either. So we stop. So in a sense here, the model that comes out is something that like yi is beta 0 plus beta 1x1 plus beta 3x3 plus epsilon I. Because this one selects x1, this one selects x3, and no further. So this model is good. It's predicting well. We don't predict so much better when we add more. But it's not necessarily the best model. And what's best here? That's hard to say. So the stepwise thing is again related to this X transpose X matrix and collinearity. When we do this, we add one. The next time we try to add others, but then we want to add things that are very collinear with X1 because X1 is already in our model. Instead, we choose maybe other things that are more orthogonal, very different from X1, because that can add more to the predictive power. And this collinearity sometimes tricks us a bit because the covariate that explains the most is not the one that maybe leads to a causal relation here, whereas it can hide a causal relation. So high SSR is not indicating any kind of causal relation. Okay, should we do this thing in Minitab just to see what is done? Then we do stat regression, and then we fit the regression model. Now I do the same, but I'll do a stepwise model with forward selection. You also see that there's something else here. Backward elimination goes the other way. Okay. And what do we get? And then you see that it starts off with it gets age and weight as the natural covariates, and then stops. And I can get more out here. If I run it again, you'll see I can get more results out. So if you check off options or results here, we can have expanded tables, and then we get some more results of what's happening here at the different stages and so on. Okay, so okay, this is what happens at the different stages. That's another thing you can expand on. And it's important to note that the R square is always going up here, and we could make R square higher. But is this R square significantly higher? That's what you ask in Stepford selection. In the end, we want then a mix of these things. We want high R squared. We want good residual plots. I didn't show that here. And we also want something called bias variance trade-off and high predictive power. And I'll quickly talk about high predictive power. Press is a residual statistic that is not working directly on the usual residuals. Instead, it's working on these residuals where we have left one out. And in particular, we have left one I out. So this is the prediction using all data. So y1, x1 transpose down to y I minus 1, but then we skip yi in this model and instead go to I plus 1. We build a model, the least squares estimator, and we fit this line using this data. And that gives us this prediction, y hat I with the ith data removed. How well is this predicting? So this is cross-validation, very commonly used in statistic to see the predictive power. And this press is then the predictive sum of squares, which can indicate how well you do outside your sample set. And here are some derivations for how you do this. When you leave one data out, you do a rank 1 update. So there's some linear algebra here telling you that you can actually get this nicely by just normalizing this residual with the hat matrix. So here you remember this H matrix, that was X transpose, X inverse, X transpose. And you can split this into H1, Hn on the diagonal. And that's used in the normalization here. So the H matrix pops up over and over again in the mathematical statistics around regression. Here's press statistic for a range of models. So you can also not just do forward selection or backward elimination. You can do the best subset in various ways in Minitab here. And here we're looking for press that is small. So which models have small press? And here we see this one has a small press, some are ridiculously large, like this one. This would not be very useful. This one is also quite small. So then we see, okay, which ones do these include in their models? So press is a good thing to also look at, not only R squared, but maybe R squared prediction as we have here, which is a function of press instead of SSE. Bias variance trade-off indicates what I talked about using this overfitting example. We want a complex model, but we don't want to have a too complex model that overfits to the data. So I think even Einstein mentioned this sometimes, or others said that you want a simple model, but as simple as possible, but no simpler. And this means that we can include covariates up to P, but P is maybe smaller than K. So P is here either 0, so this means just intercept, the mean, just mean. And then you can have one covariate in your model, two covariates in the model, and up to all covariates, which would be good models. So you range P here, and of course for each P, you can pick a range of different covariates too. Yeah, to compute this bias variance trade-off, there's something called mallow CP that's used a lot in practice. And this finds then the number of parameters. You want few parameters typically to have a simple model. So that would mean you like CP to be small, but you also want small errors. So that means you're fitting the data well. So S square and sigma hat square are variance estimates under a simpler model and under the full model usually. And these CP numbers are have some good properties again under the modeling assumptions. The bias variance trade-off then combines with other things, and here's just a printout from the book where you can look at many different numbers. Here's the R squared prediction that's computed from this press statistic. S squared, you want small variability around your line. Press and CP, and you want to look at all these things and residual plots to see what's happening to find a good fit. Here's an example that is just used to illustrate this thing. It's heat in cement mixtures, which is important for construction and stability of constructions. There are 4 covariates, 1 response. And then we can compute in Minitab many different outputs and select, okay, which model gives you the best fit. And again, we do a comparison of many numbers here. So here is R square is really good here. Oh, this is R square adjusted. That's a slight normalization of R squared. R square is high here, even higher here. But then again, when you have these high numbers, you might have, well, you also have good prediction here. So these are maybe good numbers. But the press, everything looks good down here, but not the CP, which is smaller here. So you combine this, and then on top of this, you would have residual plots to compare different results. How well is the model assumptions working here? Okay, thank you for joining this session.